Hi all. In this video, we see a paper titled End-to-End Learning for Self-Driving Cars from the NVIDIA Corporations. So in this paper, they trained CNN convolutional neural networks to directly map the raw pixels from a single front-facing camera to compute the steering commands. So bypassing like an explicit decompositions and directly train an end-to-end fashions, and so they put together all the processing steps like behavior planning, motion planning, path planning into a single step, and they train this end-to-end deep learning framework to compute the steering command for self-driving car using an NVIDIA and a Touch 7 framework. So CNN has an important advantage. Prior to this artificial neural network, machine learning algorithms important characteristic would be uh, compose handcrafted feature extractions and then followed by a classifier. But the advent of deep learning, this feature extractions has been set automatically from trained examples, and convolutional neural network is especially applied to the 2D nature of the images, which can give another further advantage of relatively a few parameters need to be trained compared to the total number of operations. So this development has given because of two things. One is availability of a large data set, and the second thing is massively parallel graphic processing unit. And the third I would like to add is the way the CNN can be trained without this gradient uh, explosion or gradient zeroing problem during a back propagation training algorithms. So the one of the key advantage here would be is that entire learning of the building of the autonomous driving is pipeline to a single systems, like directly mapping the raw pixels to steer an automobile. So this attempt has been done earlier during the time of 1989, build a system using artificial neural network, and there were also an attempt to build a system called Dave for the Durban Urban Challenge, which they trained hours of human driving based data and giving the input from the video from two cameras. So this attempt in this paper is modification of the day one, and they termed this as a day two. And one of the advantage would be to utilize the modern architecture of NVIDIA and the uh, training and CNN algorithms. So, and ultimately, the aim of this uh, objective to train this autonomous vehicle is to avoid human designated features like using land markings, guardrails, and also to avoid having to create making a set of handcrafted human based logic using else conditions. So the figure one shows a simplified block diagram. Like this is an NVIDIA processor, and we have this camera to be input, and also human based driving also given as an input, and this time stamped video is taken as an input along with the a steering command computed by the human driver, which is taken from the canvas data, and the steering calculations is fed as a turning radius, which is fed in terms of 1 by r instead of giving r, because to in a straight line the r would be infinity. So the training data, as mentioned earlier, it contains a single image sample from the video paired with the corresponding steering command, which is represented as a radius of curvature like 1 by r. So in order, this human driving data is only for the lane driving, but what would be the off if it goes off road or coming out of the off road? That is like kind of a pre-processed using some artificial rotations and translations, and that also fed during the data to identify whether we are driving along the lane or not. So this is the architecture, and we take the data from there. We make some kind of pre-processing in order to make sure that it is driving along the lane, and it also makes sure to identify whether we are going off lane. Then it is fed into that CNN, and this CNN is being trained based on the steering command, which is recorded during the CAN bus during the human driving. And this the CNN is trained in order to minimize this error, and that error minimization training algorithm is backpropagation. And through backpropagation, that weights are adjusted so that the error is minimized. So during the testing time, only the center camera data is taken into the CNN, and those weights are frozen based on the training process, and the computer output be given to the drive-by-wire for computing the desired steering value. And data is collected in a wide variety of networks and wide variety of lighting conditions and weather conditions. And this has been collected during by the same vehicle, which is having a drive-by-wire test vehicle. And the network architecture is it has a convolutional layer network which has 9 layers. The first one is a pre-built normalization layer and 5 convolutional layers. The first 3 layers have a stride mechanism, and the last 2 layers doesn't have a stride mechanism. And the first 3 layers have a 2x2 stride and 5x5 kernel. And the last 2 layers have no stride mechanism, only 3x3 kernels. And the last 3 layers are fully connected layer to train the 3 layers to this convolutional layers are assumed to extract the features, and the last 3 layers are trained to compute the steering angle. So these are the data, how the data are being human, that video collected is being processed, and that has been fed into the training process. And additional to that collected data, we also have some arbitrary random shifting in the rotations to in order to identify whether we are going off the track of the road. So before putting the train network into a actual vehicle, they try to see its performance in the simulation framework, and then the efficiency of the framework is been detected using this evaluation metric, that how many number of interventions it took for that in the simulation setup to put back like a human interventions have been utilized to put back into the normal track. So it normally takes like 6 seconds to put the off when the vehicle is going off. It is taking almost 6 seconds to put back into the normal mode. So how many times that has been during that particular time interval, like elapsed time, like say like 600 seconds, how many times the human intervention has happened to put it into a normal mode, that will give you some kind of efficiency. They claim that it is almost like 98% during the train, 90% during the simulation time. So they were confident enough and put it in the road test, and they claim that it seems to be performed very well, and drove almost like 10 miles on a parkway, and also they have put it on a highways, which gave some kind of a promising results. And they also showed some visualizations that what was happening inside the convolutional neural networks. But this says that during the off-road, that features were not properly enough to maneuver in the off-road tracks. And the final conclusion is, yes, this is a nice attempt to bypass the like kind of explicit human handcrafted layers like behavior planning, motion planning, path tracking, and using RNDFs. All those things have been bypassed, and try to compute the steering directly from the camera data. So this is not a first attempt. This attempt hasn't been done even during the time of 80s, and they were tried to adapt those things into a modern architecture, like using NVIDIA parallel architecture and the Torch 7 and the CNN networks. And they claimed that it could be able to perform very well without decomposing the process of autonomous driving into landmark detection, semantic abstraction, path planning, and control. So hope one of the next attempt for this paper is to improve the robustness of the train networks, to find methods to verify the robustness, and to improve the visualization of the internal processing steps. Thank you.